Good morning all. So my name is Leayah, Lorraine, Leano, and my research topic was upcycling polymer nets and spent coffee. Okay, so I aim to investigate how practical is the reformation of industrial and commercial waste into value-added building industrial products based on mechanical performance. Okay, so my interest in sustainability began when I was 15 because my Year 9 science teacher showed us a documentary on plastic waste. And I don't have 40 minutes to convince you to care about the environment, so I'll just jump straight into it. The effects of human activities on the environment have obviously been becoming increasingly evident over the last decades. So you have natural disasters increasing in frequency and severity, and you have plastic waste being found everywhere. So microplastics have been found in widespread and deep locations, such as the Mariana Trench, the Antarctic ice, and even our own drinking water. So this has obviously been exacerbated by burning fossil fuels, urbanization, and agriculture. So in 2017, Australians' built environment accounted for 18.1% of all carbon emissions in the nation, and it accounted for 23% of the plastic waste produced in 2019. So with continuous population growth, this will obviously increase the demand for commercial and urban buildings, which obviously emphasizes the need for less wasteful practices in the sector and prevent further waste generation. In 2018, 164 million bags of coffee were traded globally, but it has no kind of use or disposal regulations. So obviously, more methane gas is released as more coffee waste enters landfills. Another danger of coffee waste is if it enters water sources, it could lead to marine eutrophication, where excessive nitrous compounds can result in excessive growth of plants, which deplete the oxygen levels in the waters and could lead to all aquatic life kind of dying, making it a dead zone. Similarly, with abandoned fishing nets, it leads to a process of ghost fishing, where the nets fall to the ocean floor and collect all of its aquatic life. And as it takes years for this plastic to degenerate, obviously it's killing more life and will only lead to more danger and plastic waste in the oceans. So I kind of wondered what if there was a way that emerging research could show possible ways for the building sector to introduce new applications for this waste at their end of life, which would obviously tackle currently limited recycling options. So I researched how spent coffee grounds, SCGs, could help in this, problem. So I found that it would be a promising biowaste for various applications. A study showed that its microscopic composition and its high compressibility showed that it could possibly be used for absorbing medium to high sound frequency, which would make it a possible precast for noise walls. It would also have antimicrobial and antifungal properties when it is exposed to hot compression, which would increase its resistance to biodegradation. And finally, it was also found that as an increase of SCG content in panels increased, its thermal conductivity decreased. So this would make it possibly a alternative for insulation building panels. So as affordability is favored in the construction industry, its great abundance and easy treatment process could make it possibly economically beneficial. And this would provide incentive for fast integration of the material into the building industry. So for polymers, an experiment showed that as polymers were exposed to thermal decomposition, it was reduced to its monomers, and monomers are what essentially makes up polymer chains. So this proposed its high recyclability into new products for the building industry. And finally, one of the main polymer materials for fishing nets is polyethylene, which is PE plastic. And it's known for having high durability, corrosion resistance, water resistance, and easy manufacturing. And because of these desirable characteristics, obviously this has naturally enhanced its demand and production rate for the fishing nets. So all this research led me to choose the hypothesis that if a biocomposite panel contains a lower ratio of coffee to polymer, its response to mechanical tests will prove it to be a viable building product alternative. So I first conducted an FTIR analysis on the abandoned fishing net polymer to determine its main polymer type, and the resulting spectra corresponded to that of PE plastic. I then ran a TGA analysis on the sample to determine at what temperature the PE would begin to disintegrate. and the results showed that the panel making must not exceed 260 degrees centigrade. Next, I used dehydrated SCGs and shredded fishing net that was weighed and separated into 2 different trays. So one was 20% coffee and 80% polymer, and the second one was 40% coffee and 60% polymer. And each underwent the hot press machine to create the 2-panel scene. Next, a 3-point flexural test was conducted to investigate each panel's response to the modulus of rupture and elasticity. So to determine its viability in practicality, I used the ISO standards for general purpose particle boards. So the table on the left shows that the modulus of rupture for the first panel, 20 to 80, was 29.62 MPa, which is the unit of pressure megapascals. And the second panel, the 40 to 60, exhibited a strength of 27.96 MPa. So as you can see in the second table, the strength for my specific dimensions was a 6.7 millimeters in width. The requirement is 10.5 MPa. So obviously, both did successfully exceed the requirements. I conducted a t-test to determine if the difference in these 2 performances was significant, and it was found that no, they were not. Okay, so as both ratios did exceed the requirements, it opens up possibilities for biocomposites to be used into value-added building product alternatives. For example, different colors of fishing nets could be used to produce different colored products, like tabletops and the things that you use in the kitchen, the things that you open. Yeah. And obviously indoor construction projects. So as I already said, the previous knowledge of SCGs having the ability to decrease thermal conductivity and have good noise compressibility propose it for soundproofing walls and insulation building panels. And my experimental results affirmed that it would be viable for these building applications. So overall, I could say that perhaps one of the most effective means to preventing greenhouse gases and reducing human waste would truly be to reduce, reuse, and recycle. Thank you.